Okay, right. So question number 5, we will look at part 2, but actually you will need to use the data from the previous part of the question. So you are given the current, which is your I, symbol I, time, which is your T, and then you've got the initial mass of copper and final mass of copper. If you notice that the mass of your cathode has increased, that means you have produced some amount of copper. Okay, so if you just take the final mass, subtract the initial mass, you should be able to work out the mass of copper produced. Okay. The question use this data and relevant information from the data booklet to calculate a value of L. Now this one this is actually under calculations under electrolysis, which is the very first, the early part of this topic. So if you still remember, the symbol L stands for Avogadro's constant. Okay, the questions say, use this data. That means you actually have to use the experimental results to find Avogadro's constant. So it would be a little bit silly for you to write down or to answer Avogadro's constant is 6.02 times 10 to the power of 23. Okay, so what are the relationship or what are the expressions that we can remember from this part? Is the expression Q equals to IT, where Q is the charge or the electricity that flows in your electrolysis setup. And you also have this expression where F is the amount of charge carried by 1 mole of electron. So I'll just recap this quickly. F is charge carried by 1 mole of electrons, whereas E is the charge carried by 1 single unit of electron. Okay, so it makes sense. If you know the charge of one person, 1 unit of electron, then to find the charge of 1 mole, you just take the charge of a single unit of electron times by the number in 1 mole, and 1 mole is 6.02 times 10 to the power of 23. But our goal is to find L based on the results of this electrolysis experiment. Okay, so E, the charge of electron, is something that we cannot measure experimentally, but it is given already in your data booklet. It's the first page of your data booklet where it says electronic charge. That is the charge for 1 single electron, and you notice that there is the negative charge, but when you use it in calculation, you do not use you leave out the negative charge. Okay, so the charge of electron is 1.6 times 10 to the power of minus 19. Okay, so first we are going to use the information that we are given. Okay, since we know I and T, we can find Q, the charge in the experiment. Okay, so make sure T is in seconds. So you have to convert T into seconds. And because you know the mass of copper, you can find the number of moles of copper, which is mass over AR of copper. I can tell you the AR of copper is 63.5. Okay, so I'll let you find the numerical answers to these 2 questions, and I will check if it agrees with the marking scheme. Okay, Hazira is here.
Yes, which question are you?
Question 5, sorry. We are looking
Okay.
at question 5, part 2.
Okay, thank you.
You're welcome. Okay, so your Q, after you convert the time, should be 900 coulombs. Okay, and then the number of moles should be 4.71 times 10 to the power of minus 3 mole. So usually when it comes to calculation involving electrolysis, it will come to a point where you don't know what to do, where to start. Okay, if this happens in the exam, you just use the information that you are given and try to find whatever you can from there. Okay, so macam this one, I and T, you know that if you know the I, if you know the T, you can find the Q, which is the charge. Okay, another thing that you need is the half equation. Okay, so you need the half equation. The reason why we need half equation is because in order to form 1 mole of copper, we require 2 moles of electrons. Okay, so this half equation is useful in a way that we know how much electrons is needed to produce 1 mole of copper. But here we've got that 4.71 times 10 to the power of minus 3 mole. Now, why are we interested in electrons? It's because electrons is our current or electricity carrier. Okay, electron carries charges. So what we can say is that when we use, okay, if we use 900 coulombs of charge, we manage to produce 4.71 times 10 to the power of minus 3 mole of copper. Okay, we want to know how much charge is needed when we produce 1 mole of copper. Okay, so we do that first, and then you may be asking, like, why do we need to know how much charge is required for 1 mole of copper? Because copper and electron is related to each other because electrons carry charge. Okay, so hopefully later on, after we're done with the question, I will explain to you again why we have decided to do these steps. Okay, so first you want to know the charge that is required to produce 1 mole of copper. Okay, I got 191,489 coulombs of charge to produce 1 mole of copper. Okay, and if you look at the equation, this is where the half equation comes in. 1 mole of copper requires 2 moles of electrons. That means to produce 1 mole of copper, I need a charge of 2 moles of electron. Okay, and here I already know that to produce 1 mole, I need this much charge, 191,489 coulombs. Okay, so do you all agree that this charge is equals to 2 mole of electrons? Okay, I repeat, here it says that to produce 1 mole of copper, you need 2 moles of electrons, right? And electrons is a charge carrier. Okay, so if we say that to produce 1 mole of copper, 191,489 coulombs of charge is required to be supplied to produce 1 mole of copper. Okay, so, and this is equivalent to 2 moles of electrons because of the half equation. Now, where am I going with this? Why am I now looking at 2 moles of electrons? Hello, Ridwan. We are now looking at question number 5, okay, of exercise 24, question number 5. Okay, so if you go back to our expression, and if I just remind you again, this question actually wants you to find L. Okay, if I rearrange the expression F equals to LE, to find my Avogadro's constant, I need F over E. Okay, and as I mentioned earlier on just now, E is the charge of one single unit of electron, which cannot be found using an experiment, but F we can find using the experiment. Recalling, F means the charge of 1 mole of electron. See, this is the charge of 2 moles of electrons. So to find the charge of 1 mole of electron, which is what your Faraday's is, okay, you have to do this. 191,489 coulombs is associated with 2 moles of electron. So how much is 1 mole of electron? Okay, in theory, 1 mole of electron, which is Faraday, is about 96,500. You will see that based on this calculation, because we use data from the experiment, it will not be exactly 96,500. Okay, it will be slightly not too far off, but it's not the exact amount. Okay, so it's the same as dividing 191,489 divided by 2. That means the charge of 1 mole of electron is equals to 95745 coulombs. Okay, and in theory, our Faraday's is 96,500. Okay, then only, okay, yes?
How did you get 191489?
Okay, that is from here. So
Um,
if I use 900 coulombs of charge, I get 4.71 times 10 to the power of minus 3. Okay, but I want to know how much charge I need if I want to produce 1 mole of copper. Okay, so that's where I get my, yep.
Is your calculation correct? I got different value.
So 900 divided by 4.71 times 10 to the power of minus 3. 191,082. Did you get that?
yes.
Okay,
Yes.
all right, sorry. That means I copied blindly from the marking scheme. Okay, but same thing, 191,083 coulombs. Okay, thank you for pointing it out. I just used the value from the marking scheme. Sorry about that. 191,083 coulombs, but the working is still the same. Okay, so that means my Faraday's, the charge per 1 mole of electron would also be different, slightly different, but not too far off. 95542 coulombs. Is that okay? Okay. Going back to the actual question, L is F over E. Okay. My F, I can find F experimentally, which I just did. Okay. I compare. If I want to produce 4.7 times 10 to the minus 3 mole of copper, I would need 900 coulombs of charge. And if I want to produce 1 mole of copper, I need 191,083 coulombs. Okay, and 1 mole of copper is equivalent to 2 moles of electrons. Okay, so that means this number, this charge is associated with 2 moles of electrons. F here is the charge of 1 mole of electron. That's why I have divided it by 2. And also it should give you a warning if your F, the value of F, is not anywhere near 96,500, which is the constant value of F. That means there's something wrong with your calculation. Okay, so it has to be close to 96,500. And your final answer would have to be close to 6 times 10 to the power of 23. So if we take our experimental Faradays, which is 95542 over 6.02 times 10 to the power of 23. Oh my God, what am I doing here? Sorry, wrong. It has to be the single charge of the electron, which is 1.6 times 10 to the power of minus 19. 1.6 times 10 to the power of minus 19. If you're wondering what this number is, the E is the charge of a single electron, which is 1.6 times 10 to the power of minus 19. And that can be found on the first page of your data booklet. So I got 5.97 times 10 to the power of 23, which is close to 6 times 10 to the power of 23, which is your Avogadro's number. Okay. Okay. I will leave the screen here. If you still trying to absorb this and you haven't finished copying, you can take a screenshot of this. Okay. Otherwise, those who are done with the calculation can move on to question 6.
Miss, why is the electronic charge positive 1.6, but in the data booklet it says negative 1.6?
Okay, so the negative, we don't want, the negative is just Kira to tell us that electron is a negatively charged, okay? But here we want to use the magnitude only, the size. If we use negative, our Avogadro's constant will be negative, which doesn't make sense. Okay, so that's why in calculation, sometimes we just drop the negative sign. And also because if we say that, if we talk about charge, well, charge is okay to have a negative, but it's just that in this case, we can't have a negative Avogadro's number. Okay, so just take the sign as about the positive and the negative charge. All right. Okay. Are you all ready to move on to question 6? Okay, now let's move on to question 6. Right, most of the current that passes through the cell is used to dissolve the copper at the anode and to produce copper onto the cathode. So we are still using the same half cell equation, which is copper 2 plus 2 copper solid. However, a small proportion of it is wasted. Okay, so we'll deal with that first. We highlight the information that is given. Current 20 amps, time, which is 10 hours. You need to convert that to seconds. It was found that this mass of copper is being produced. Okay, so we follow the what the question is asking for. Some questions are nice where they break down your working. If you get a question like this where they don't give you any supporting questions, that's difficult because you don't know where this is going. You don't have direction. So first question, they want you to find number of moles of copper produced at the cathode, and that's a simple mole calculation. So to find number of moles of copper, you take the mass of copper over the AR of copper, and the AR of copper is 63.5. Okay, so that answer should be 3.54. Did you get 3.54 mole? Okay, right. So they want you to find the number of moles of electrons needed to produce this copper. That means to produce this much or this amount of copper. This is where your half equation comes in. Your half equation tells us that if you want to produce 1 mole of copper, you require 2 moles of electrons. Agree? Okay. But here we are producing 3.54 moles. So how many moles of electrons would be needed? Okay, so we use this ratio to form 1 mole of copper. We need 2 moles of electron. But in our setup, we actually produce 3.54 moles of copper. Oops. 3.54 mole of copper. So how many moles of electrons would be required? So it's just 2 times 3.54. Okay. 7.08 mole of electrons needed. Is that okay? Can follow? Okay. Number of moles of electrons that pass through the cell. So this is the number of mole of electrons required to produce this amount of copper. Okay, we want to know the number of moles electrons that pass through the cell. That means we need to find the electricity going around the cell first. Okay, first we start with the easier. Q is equals to IT, where T has to be converted to seconds. I is 20 and your T is 10 hours. So you should get 720,000. Okay. Okay. So we are going to compare, or we want to quantify this charge into moles of electrons. How many moles of electrons would give us this charge? Okay. Here's one concept that you need to remember. In 1 mole of electron, there is 70 berapa Faradays? How much is Faraday's again? Just now I remember. Faraday's 9.6. Okay, 96,500. So in 1 mole of electron, there is 96,500 coulombs. Okay, we want to know how many moles of electron this is associated with. Mole of electrons. So we can build the relationship. Okay, so 96,500 is 1 mole. How many moles is 72000 coulombs? So that means 720,000 is equivalent to 7.46 moles of electron. So you can talk about charge in the form of coulombs or in the number of moles of electrons. It's the same thing. If we say in this setup, I have 1 mole of electrons of charges, it means that I have 96,500 coulombs. Okay. If I say in this setup, I have 3 moles of electrons, the equivalent charge would be 96,500 times 3. So the reverse is also true. 1 mole of electron would carry 96,500 coulombs, and 720,000 coulombs is equivalent to 7.46 mole of electrons. Okay, so where are we going with this? This number, 7.46 moles of electron, is the charge that is being supplied into your electrolysis setup. Okay, 7.46. However, only 7.08 mole of electrons of charges is being used to produce the copper. So that means you have some extra electricity, extra current that is not being used to produce your copper. And this extra electricity is thought as being wasted, okay, because some of this electricity is not used to produce copper, but it is used to dissolve impurities in the anode. So that means it influences other reaction, not the production of copper, just other things. Okay, so to find the percentage waste, so it's like this is what you are, the electricity or the current that you are supplied with, but this is the current or electricity that you used for the reaction. Okay, so that means to find the percentage of current wasted or electricity wasted is equals to 7.46 minus 7.08 over the total of current you are supplied with. Okay, so this kind of question is not in your notes, but because the calculation, if you look at the calculation, these are things that you know or they think that you can make sense of. Okay, that's why they will throw at you different format, different calculations, and you may argue and say, but we've never done a question like this. That should come out as 5.10%. Okay, so that's for question 6. If you think you will need time to think about that question and digest the information, you can take a screenshot first. And then later on, as you copy along, hopefully you are able to understand what we are doing here. If you're done with this, you can start reading question 8. So question 8 and question 9 is similar. So if you notice on question 8, you are looking at the production of hydrogen gas, okay? And it is at the cathode. So you will need the half equation that involves hydrogen gas as well as hydrogen ions, okay? So there is a half equation that involves H plus and H2, and you will need that for later on at one point. Same thing. This time the current is not given to you, okay? The current is not given to you, but the time is given to you and the volume of hydrogen gas. Okay, so I'll move on to question 8 now. Okay, so you notice that I have already prepared my half cell equation. So I don't know the current, I know the time, I know the volume of hydrogen produced at the cathode, measured under room conditions. Okay, so that means at room temperature and pressure, you must remember this: 1 mole of any gas will occupy 24,000 centimeter cube of volume. All right, so calculate the number of hydrogen molecules produced during the electrolysis. So to find the number of hydrogen molecules. Okay, so that means you want to find the number of moles of hydrogen first, okay? And then only the actual number of hydrogen molecules. Okay, so to find the number of moles, you take your volume, divide by 24,000. Okay, please do not use the formula N equals to C over V. You do not have concentration here. Okay, and it is a gas, therefore we use the concept of 1 mole of any gas occupies 24,000 centimeter cube or 24 dm cube. So that's 462 divided by 24,000. And that should come out as 0.019 mole. Okay, now the question is not asking you for the number of moles, otherwise it would mention the number of moles. Here it says the number of hydrogen molecules. So they want to know how many molecules are there in 0.019 mole of H2 molecules. So the number of hydrogen molecules is equals to number of moles, N, times by the Avogadro's constant, okay, which is, I will just write down as L. Otherwise, you can just take your 0.019 mole times by 6.2 times 10 to the power of 3. And that gives you the number of hydrogen molecules in 462 centimeter cube, which is also equivalent to 0.019 moles of hydrogen molecules. So what's the difference between number of moles and number of hydrogen molecules? Okay, in 1 mole of hydrogen molecule, there is 6.2 times 10 to the power of 23 hydrogen molecules. So there is a difference, the mole and just the number. Just like me asking how many eggs are there in 1 dozen of eggs. Okay, so in 1 dozen of eggs, there are 12 eggs, 12 units of eggs. So this is what the question is asking for. How many units of hydrogen molecules are there in 0.019 mole of hydrogen? Okay, so that comes out as 1.17 8 or 1.18 is also fine. 3 significant figures times 10 to the power of 22. Now be careful with your significant figures. I have been very careless actually, because I don't watch my significant figures. I just leave my answers as I like it. But you have to be careful with your significant figures. Okay. Next is the number of electrons. Calculate the number of electrons, calculate the total number of electrons transferred to produce this number of hydrogen molecules. Okay, so if you look at the equation, 1 mole of hydrogen gives you 2 moles of electrons. Yeah, that means to produce 1 mole of hydrogen, you require 2 moles of electrons. But we know that in this setup, we did not produce 1 mole of hydrogen. We only produced 0.019 mole of hydrogen. So how many moles of electrons is that associated into? So that means to produce 0.019 mole of hydrogen, you need double that amount. 0.38 mole of electrons is required. Are you all okay so far? The relationship in the equation, half cell equation, is important. Okay, but the question is not asking about the number of moles of electrons. They want to know the number of electrons. How many units of electrons are there to produce 0.019 mole of hydrogen? Okay, so that means the number of electrons required per 0.019 mole of hydrogen is equals to number of moles of electron times by the Avogadro's constant. Okay, same thing, 0.38 mole times by 6.2 times 10 to the power of 23. Okay, so it's 0.38 times 6.2 times 10 to the power of 23. You may be wondering, why do they want our answers as numbers, as units of electrons, as units of molecules? Because we usually just leave our answer in mole. Okay. The reason for this is because 2.256 times 10 to the power of 23. The reason for this is that,
Miss,
yes.
is it 0.038?
Thank you. It might be. Yes. Thanks. 0.038 mole. So that means I made a mistake again here. 0.038 times 6.2 times 10 to the power of 23. Thank you for correcting me. So it should be times 10 to the power of 22. Okay. So this is good. At least I don't have to text you and correct myself like what usually happens if I record myself and just send you the video. Okay, calculate the quantity of charge of the total number of electrons calculated in B. Okay, so this is how much electrons we have. Again, you can see my significant figures is so out of place, out of the window. So we want to know how much electrons, how much charge is carried out by this amount of electrons. Okay, so we know that, oops. Oh no. Okay. If one single electron has a charge of 1.60 times 10 to the power of minus 19, what is the charge, coulombs of charge, okay? What is the charge when we have 2.356 times 10 to the power of 22 electrons, okay? We want to know the exact charge we have, the exact amount carried by the electrons that we have in the setup. So in order to find that, we just multiply it, 1.6 times 10 to the power of minus 19, okay? So that means you have x is equal to 3770 coulombs of charge. All right, now if you go back, that means to produce 0.019 mole of hydrogen, which is 462 centimeter cube of hydrogen, the charge required to produce this much is 3770 coulombs. Calculate the current X passed during this experiment. Then only you can find Q equals to IT because you know the charge Q, you know the T, which is 14 minutes. So you can find I. You cannot simply find the current without knowing how much charge there is flowing in your setup. Okay, so I'll let you work out your I, making sure that your T is in seconds. And that is the most important. If you forgot to convert it, then of course your answer will be wrong. Q is
Miss?
yes.
Yedi said your Avogadro constant is wrong. It's 6.02, not 6.2.
Thank you, Yadi. Why you didn't say anything just now? Artinya dari tadi ke to?
Iya toh.
Well, I don't want to change it now, but you know that it's Avogadro's constant, okay? Why you didn't say anything just now, Yadi? So I've got my Avogadro's constant wrong, but that number represents Avogadro's, okay? Thank you for pointing it out and sorry about that. This one, Avogadro constant L, 6.02 times 10 to the power of 23. Okay, I don't want to change my number. If you want to change your number, you can. But the working is still the same. Okay, everything, the steps are still the same. Okay, so I'm just going to move on using my made up Avogadro's constant. Okay, maybe I should change it. I no longer call it Avogadro's. Maybe I call it Rabi's constant or something, since I made up that number. Going back to part D, I want to find my current because my current is at the moment X. That's my unknown. My Q, I found that it's 3,770 divided by the time, 14 times 60. So I got 4.49 amps. Did you guys manage to get that? Okay, I'll give you time. So I'll just zoom it out. Is that everything? Yeah, you should be able to see everything here. Okay. Did you manage to get the answer, 4.4? In the mark scheme, the answer is also 4.4. So I think even though we use a slightly different value of Avogadro's constant, it doesn't change the answer much. Okay, just in marking scheme, it's still 4.4. That is if I do the correct calculation correctly lah. Are you okay to move on? Last question we will look at for today will be question 9. It is similar to question 8. All right. I'll let you read first for just to give 1 more minute on this slide. Can move on, huh? Yeah, all right. I can see that everyone is flipping their page already. Okay, pure water, overall change. Okay, so I will just skip and go straight to the given information. I know my current I is 3.1 amps. Is passed through the solution for Y minutes. So this time my T is unknown. Okay. 351 centimeter cube of chlorine are produced. So that means that's my volume. Volume of gas, chlorine gas. And remember that 1 mole of gas, any gas, occupies 24,000 centimeter cube of a container. Calculate the number of chlorine molecules. So again, same thing, they say number of chlorine molecules, not number of moles. But before we can calculate the number of chlorine molecules, of course, we have to find the number of moles first. So number of moles of chlorine is 351 over 24,000. You take the volume over the molar volume, if you still remember from topic 1 last year. So I got 0.0146 mole of chlorine. But the question wants me to find the number, the actual number of chlorines in that 0.0146 mole. Okay, so number of chlorine molecules is equals to mole times Avogadro. So this time I'm going to use the correct Avogadro's value. Correct, yeah, day 6.02 times 10 to the power of 23. Okay, he's just smiling. So artinya dari tadi Miss Salah, he's just smiling and laughing at me. See, he's laughing again. Okay. So that means the number of chlorine molecules that I have in this 351 centimeter cube of container is equivalent to 8.79 times 10 to the power of 21 chlorine molecules. Did you get that? Okay, good, thank you. Calculate the total number of electrons transferred. Okay, so based on this equation, it says that to produce 2 moles of chlorine, you require 2 moles of electrons, which is just 1 to 1. Yeah, can you see that the number of moles of, sorry. Oh, it is not 1 to 1. Chlorine is Cl2. Oh, there we go. I almost made that mistake. I think I made that mistake that day. Oops, I did. 1 mole of chlorine is equals to 2 moles of electrons. Okay. Okay, so to produce 1 mole of chlorine, I require 2 moles of electrons. And my number of chlorine here is 0.0146 mole of chlorine. So how many moles of electrons will be required? So that means it's 0.0146 times 2. So number of moles of electrons required is 0.0292 moles. Are we okay so far? Okay, so but they don't want number of moles, they want the total number, the how many units of electrons. Okay, so that means to find the number, oops, sama juga, number of electrons is equals to number of mole times by Avogadro's constant. That is 0.0292 times by 6.02 times 10 to the power of 23, which is 1.76 times 10 to the power of 22 number of electrons. Of course, electrons as electric or current carriers, we want to know how much charge this is equivalent to. Okay, so we know that for one single electron, the charge is 1.6 times 10 to the power of 19 coulombs. So how much charge is carried out by 1.76 times 10 to the power of 22 electrons? So you just multiply them. 1.76 times 10 to the power of 22 times by 1.6 times 10 to the power of minus 19. 2816 coulombs. That means in this setup, there is actually 2816 coulombs of charge being supplied. So once you know the charge that goes in your setup, you can then work out your T. So T is equals to Q over I. Remember that T, your answer is in seconds. Okay, so you have to convert it to minute as requested by the question. What's our current? 3.10 amp. So that is 908 seconds. Okay, whatever your answer here is in seconds. Sorry. But the question wants in minutes, so you have to divide it by 60, and that comes out as 15.1 minutes. Is everyone okay with this? Lengthy calculation, I can assure you, if you think your stability constant Ka, KSP, KPC are difficult, I think that electrolysis calculations are much more difficult, okay? Because you cannot visualize it. Like, it's confusing to be talking about the charge of 1 mole of electron, the charge of a single unit of electron, and apa lagi tu? Yeah, things like that. I think it's not a common concept for students to understand. Okay. Right, so is everyone okay with this? Done? Any questions? Or did I make any mistake along the way that you did not say anything? Okay, so in that case,